This lesson deals with a high-frequency model of a MOSFET. You can find these notes in the ECE302 ebook in Chapter 10, starting on page 43. What's shown below here is a large signal SPICE model for an NMOS transistor. What's been added since our previous model is a resistance associated with each of the wires coming into the transistor, a capacitance associated with the diode, and also capacitances between the gate and drain, gate and source, and the gate and bulk. There's also been a resistor added in parallel with the current source. The equations for the diodes are just our Shockley equation. They're both about the same size in manufacturing, so the etas are about the same. Our equations for cutoff, ohmic, and saturation are very similar to the JFET, except for the following. We've now added a width over length, and this refers to the width and length of the channel or the gate. We're using the term V threshold in our previous modeling, but in SPICE this means something quite different, and we'll see the definition on the next page. We have a reverse bias diode, then we have a depletion capacitance, and that's our expression that we had previously, with a transition between forward bias and reverse bias. There's also a forward biased equation built into SPICE, but we're normally going to reverse bias these diodes. The capacitances between the gate and the drain, the gate and the source, and the gate and the bulk are called overlap capacitances, and they're due to the overlapping of two conductors separated by a dielectric, which is the oxide layer. There's a constant here, which is farads per meter, times the width or the length of the channel. This term V threshold is now VTO, which we had used before, but now a term is added with a bulk to source voltage. The width and length are the effective channel width and length in meters of the transistor. VTO is the value of the threshold voltage when the bulk to source is set equal to 0. So when this is set equal to 0, these two cancel. And that was the case we had before, where we shorted the bulk to source. But when you build an IC, that won't necessarily be true. The term gamma in this equation is called the bulk threshold parameter. And then lastly, this term phi, called surface potential, has the units of volts, and it's not the built-in barrier potential we talked before, phi 0, but another term. The large signal SPICE model for a PMOS transistor is the same as the model we had on the previous page, except I'm going to label this as I sub dP. This is going to be the drain current due to the PMOS transistor. The one previously had an N here. Everything else is the same, except the diodes are reversed. And we'll see with our equations on the next page that although these definitions haven't changed, we'll have sign changes in the formulas. What are shown here are the equations for the P-channel model. They're similar to that on page 43, but every voltage and every current has a sign change. And I've marked these in yellow, as you can see here. For this equation, I changed the sign of this and this. This was a plus sign here, and I multiplied through by -1. It's also interesting to note that gamma and phi are both positive for P-channel and N-channel. As mentioned before, VTO is positive for an N-channel device, and VTO is negative for a P-channel device. We next need to convert our equation notation to SPICE notation. The first few terms here we've had before, we've had I sub S as IS, eta as N, 2K as KP, and VTO as VTO, with the default values shown here. Now what we've added is width and length, and the default values are 100 micrometers. So their ratio shows up in the equation, so they had no effect before because the default values were giving a ratio of 1. But now as you design ICs, we play with the width and the length of the channel to adjust some of the parameters. We've also added lambda, which has units of 1 over volts, gamma, which has units of square root of volts, phi has units of volts, and the default values are also given here. Likewise, we've added resistors in the series leads of the transistor. Those just become the same letters without a subscript and are all defaulted to 0. There is a resistor added in parallel with the current source, and this is defaulted to infinity, so in other words, it has no effect until you put a value in for it. And then we had an equation for a reverse bias diode, defaulted to 0, so again has no effect until you put it in. Then we had the overlap capacitances, and then their corresponding SPICE notation is the same letters but all uppercase. And then of course we've had the built-in barrier potential and the grading coefficient before. You can find more about this in the Rashid paperback from pages 307 to 312. I should point out that this is called a level 1 model in SPICE. I took some typical values for an NMOS transistor with a level 1 model and put the values here. I thought I'd go back and get the curve tracer module from chapter 4, and let's run the curve tracer on this transistor to see what it looks like now that we've added a term lambda, which will act like an increase in slope as we increase the voltage or the current. These are of course static or DC curves, so the capacitances don't show up. I'm varying the drain source voltage from 0 to 10 volts in 5 millivolt steps, and that's about 2,000 points. And then the gate source voltage from 0 to 3 volts in half volt steps. Here's the 3 volt, 2.5, 2, 1.5, 1. And then there's also 2 more here for half a volt and for 0, but those are all less than or equal to the threshold voltage. You can see there's a little bit of a tilt to the curves now. And of course we have the unequal space because of the basic square law equation. What's shown here is the AC small signal model for an NMOS transistor. What we've added since our previous modeling is that we've added capacitance between the gate and the source, the gate and the drain, the gate and the bulk to the drain, and the bulk to the source. Also added series resistances with the associated wires. Parallel resistance here, which represents our slope in our curve. And then we had a GM-VGS previously, but I'm going to add another term, GMB times V sub BS, and the reason is that the drain current is now a function of 2 variables, the gate source voltage and the bulk to source voltage, because this shows up in our threshold equation. I went and grabbed the equation from our JFET calculation where we took the derivative of I sub D with respect to VGS at the Q point and just added the width over length. And likewise for the drain to source resistance, we had derived this last time, but there's also now a resistor in parallel with it, which is RDS. We're going to add these 2 conductances together. The term GMB is the second term in that controlled source, and that's because I sub D now has another variable in voltage, and that's the bulk to source voltage. So we need to take the change in drain current for a change in the bulk to source voltage at the Q point. I could write this as a product of 2 derivatives, partial of I sub D with respect to the threshold voltage, and the threshold voltage with respect to the bulk to source voltage. Let's find this first one right here. We'll take the partial derivative of I sub D with respect to VTH, and here's my equation for I sub D. Now, if you go back and look at page 39 for the JFET, we had a pinch-off voltage here instead of the threshold. It's the same equation we took the derivative of on page 39, except that now I have a minus sign here. We're going to get exactly the same equation we had here, except there'll be a minus sign because of this term right here. This first derivative here is just equal to minus GM. Quick note, for the PMOS AC model, we're going to change the polarity of the gate source voltage and the direction of the 2 current sources, like we did in chapter 5. We also will flip the subscripts accordingly. The other term in the GMB calculation is the partial of the threshold voltage with respect to the bulk to source voltage. And this is the equation for the threshold voltage. Take the derivative with respect to this term right here, so that's going to be 0, and that's going to be 0. And then this term gamma multiplies that, and you can think of this as this quantity raised to the 1/2 power, so the 1/2 comes out in front, and we subtract 1 from a half, so we get a minus a half. And then the derivative of what's inside here with respect to V sub BS is just a minus 1. Here's the 2, here's the gamma, here's 1 over the square root, and we'll evaluate this at the operating point, which is just the value of the bulk to source voltage at the Q point. We can multiply those 2 results. We get a minus GM for the first part of the derivative, this term here. The second part, we have another minus sign. They cancel. I just get this other term over here. So we can now calculate GMB in terms of the bulk to source voltage. And then we have equations for the 2 diodes between the bulk and the source and the bulk and the drain, with a term when this is equal to 0. This all drops out, we just get this term, and likewise over here. And then we've got our built-in barrier potential and on our grading coefficient. Then we have our overlap capacitances, and they're a value of a constant times the width or the length associated with the channel. These terms here, as we begin to study more modeling in CMOS IC design courses, there'll be more terms added into here. This is going to give us an introduction as to where the capacitances are, but this is where the 5 capacitances will show up. Their values might be a little bit bigger if we put more modeling in. Shown below here is a common source amplifier. I'm going to call it wideband because I'm going to have SPICE stick in a high frequency model for the NMOS transistor. And we'll take a look at the Bode plot of V out, which is node voltage 7, divided by node voltage 2, which is V in, versus frequency. SPICE file is shown here. It's very similar to the file we'd written in chapter 5. We had an NMOS amplifier with just a low frequency model. So I'm going to stick in that model I had in the curve tracer. It's got capacitance in here and some of the terms we talked about. And I'm going to do a Bode plot from 1 Hertz to 500 megahertz with 24 points per decade, and that's going to be about 200 points total. Also going to ask for the operating point, and we'll see if some of our equations check that we had described previously. I printed out the operating point. I also printed out the model so we could see the terms that we put in that model line, but just one line at a time. This first set here are the DC operating point from SPICE's calculations, and this is used with the derivatives of the appropriate voltages and currents to calculate the AC parameters. And of course, we've got formulas that approximate this. So let's see how close we've come with our formulas. The threshold voltage was this expression. VTO is up over here as 1 volt. Gamma is equal to 0.5. Phi is equal to 0.6. But our bulk to source voltage over here is equal to 0. We had shorted those two in that schematic on the previous page. So these terms drop out and we just get the 1 volt. Now when you design ICs, we're going to hook up the bulk to the most positive potential in the circuit for a P-channel device and to the most negative potential in the circuit for an N-channel device. So we're going to get a value of voltage for the bulk to source voltage that won't be 0. And when you buy an individual transistor, that's always the case. You're going to short those two together because of this term being present. This is our formula for GM. Let's plug in the values here. K is half the value of Kp. It's 1.5 milli. The width and length were 100 micron. Of course, they're going to drop out as a ratio. The value of lambda is 5 milli. And the drain to source voltage over here is 11.4 volts. And the drain current is 1.16 milliamps. That gives me 2.712 millimos. And back up over here, it's 2.7 millimos. Our value for R0 is the value of RDS, and that was specified as 1 megohm. I purposely put that in to show that it does show up in the model. I don't think you really need this because of lambda will tilt the curves, but this is in the model for some reason, so you can specify it, and it will have an effect. R sub G over here is 1 ohm, and R sub B is also 1 ohm. This was our formula for the drain to source conductance, which is in parallel with the controlled sources, and it was this expression here. Lambda was equal to 5 milli, and the drain to source voltage and the biasing current is 1.16 milliamps, and all this together, reciprocal, is about 182.4 K. So that's in parallel with 1 megohm, and that'll give us the reciprocal of this as an equivalent resistance of 154 K. This did have an effect on the total value of conductance or eventually resistance. Let's calculate GMB. This is our equation we had previously, and we just calculated to be 2.712 milli. This was 0.5, this was 0.6, and the bulk to source was 0. And I get 875.3 millimos. Let's compare these last two to what we just calculated. Here's the term GMB, and that's 871 micromoles, and we calculated 875.3 micromoles. And we calculated GDS as being 6.487 micromoles, and here it's 6.46 micromoles. Very close with these formulas to what SPICE is calculating through a process of taking derivatives. Lastly, let's take a look at these capacitances, which are calculated based on the parameter we specified here and the width and length of our channel. The gate to source, gate to drain, and gate to bulk overlap capacitances are indicated in SPICE with an OV with that capacitance. That's just our capacitance between the gate and drain, gate and source, and gate and bulk. That's due to the scalar times either the width or the length. It's going to give us a pretty small capacitance because these are in nanofarads per meter. I get 0.6 picofarads, 1 picofarad, and 0.9 picofarads. But I also have capacitances associated with the two diodes between the bulk and source and bulk and drain. But the bulk to source voltage is 0. We just get this term, that's just 2 picofarads. But for the bulk to drain, we need the bulk to drain biasing voltage, but the bulk to source is shorted, and so the bulk to drain voltage is just a negative of the drain to source voltage, so it'd be a minus 11.4 volts. P0 was 0.8, and the grading coefficient was 0.5, that gives me 1.28 picofarads. We also have some resistances in the leads of R sub S of 2 ohms and R sub D of 5 ohms. Now SPICE is going to plot all of this versus frequency. If we ask for the output over the input, you can see here we've got a broadband amplifier with a midband gain of 18.497 dB. If you divide that by 20 and put it to the power of 10, that's a gain of 8.411. The 3 dB frequencies are at 12.85 hertz and 27.38 megahertz. You can see that the gain is negative in the midband. So we always have a minus sign with our gain like we had seen in Chapter 5. Could you use the methods that we talked about earlier in this chapter with open circuit and short circuit time constants to verify this result of the midband gain and the low frequency and high frequency corner? And this is a high frequency model of a MOSFET.